Good morning. The Subcommittee on Energy will come to order, and we welcome today's hearing entitled A Review of the P5, the U.S. Vision for Particle Physics After Discovery of the Higgs, is it Boson? Boson. I'm going to need an explanation of what that is. In front of you are packets containing the written testimonies, biographies, and truth in testimony disclosures for today's witness panels. And I now recognize myself for 5 minutes for an opening statement. I would like to welcome everyone to today's hearing on the status of particle physics research in the United States. Today, the Energy Subcommittee will discuss the strategic plan for U.S. particle physics in the global context offered by the Particle Physics Project Prioritization Panel, also known as the P5. Researchers in particle physics seek to unveil the fundamental components of existence in an effort to better understand the interrelationship between space, matter, and time. The field has been highly successful, recently yielding discoveries of the heaviest elementary particle, the top quark, the tiny masses of neutrinos, the accelerated expansion of the universe, and the Higgs boson. The P5 plan reflects approximately 1 year of deliberations to reach consensus throughout the particle physics community regarding the best opportunities for the United States to maintain global significance in this scientific discipline while considering 3 potential budget scenarios. While the U.S. remains in a state of fiscal uncertainty, reducing overall federal spending in order to arrive at a balanced budget should be a top priority. Yet during this process, we cannot overlook the fact that the federal government plays a critical role when it comes to the nation's long-term competitiveness in the physical sciences. As noted in the P5 report, the countries that lead these activities attract the top minds and talent from around the world, inspire the next generation of scientists and technologists, and host international teams dedicated to a common purpose. In particle physics, the U.S. is already slipping and stands to lose its position of global significance if we do not act boldly. Basic research, such as that which is funded through the Office of Science's High Energy Physics, also known as HEP, pronounced HEP, is proper use of taxpayer funds. As the authorizing committee of the House, we are responsible to ensure that the HEP program uses its limited funds prudently. I say this to underscore the importance of the P5, which had to make difficult choices, but found a way to achieve consensus in this very competitive area of cutting-edge science and provide the U.S. particle physics program with a roadmap for success. To the witnesses, I convey my admiration for your hard work, for those who took part in the P5 directly, and those who carry out this unique research that we will learn more about today. I want to thank the witnesses for participating in today's hearing and look forward to their testimony. A high school colleague of mine by the name of Greg Snow became part of the team that worked on particle physics. I see you nodding, and he and I were very dear friends, high school friends, and so I have followed his career and note his excitement about what you have done, and so I've lived vicariously through him following your work, and his excitement is contagious, I might say. So welcome. We are delighted to have you here. And now I recognize the ranking member, the gentleman from California, Mr. Swalwell, for an opening statement.
Thank you, Chairman Lummis, for holding this hearing. I also want to thank this excellent panel of witnesses for their testimony and being here this morning. I'm especially pleased to see Northern California so well represented at the panel, which clearly means that this is going to be a particularly informative and productive congressional hearing today. And that is not, of course, to take anything away from Dr. Locke here. We're here to discuss the recently released P5 report, which lays out a vision for particle physics in the United States over the next decade. The timing of this report could not be any better, as we are extremely excited about the history of this field. With the major advances that have been made over just the past couple of years, such as the Nobel Prize-winning discovery of the Higgs boson, as well as the potential detection of gravitational waves, first predicted by Einstein 100 years ago, we are equipped with knowledge and advancing technologies that will allow humans to further engage on our innate curiosity about everything from fundamentally building blocks for the world as well as to the origin and the evolution of the universe. However, as amazing as these developments may be, and as much as we would like to continue to push the frontiers of science, we are also forced to keep in mind our currently fiscally constrained environment. This is the reason for the Department of Energy and the National Science Foundation charging the P5 panel with doing the hard work of prioritizing particle physics projects under several difficult budget scenarios, the lowest one being particularly restrictive and, in my view, unacceptable given the critical missed opportunities that would be required to meet it. I also believe that the end result is a very strong product, and I want to thank Dr. Ritz for his leadership and the P5, as well as the entire P5 team for their efforts. Tough decisions were obviously being made, especially considering the long-term nature of building operating particle physics facilities. The Higgs boson I mentioned earlier was found using the Large Hadron Collider, which took 10 years to build and will continue to operate well into the next decade. And in fact, the Higgs boson's existence was first projected and postulated 50 years ago. This gives us an idea of how far out the P5 had to look when working through the prioritization process. And what they produced provides policymakers with sound guidance, which we should in turn use to provide the particle physics community with the support and stability it needs to conduct complex, long-term research that will help us understand far more about the nature of our universe. The United States has a long history of leadership in advanced physics, and I think that we have been presented with a report that will ensure that this continues to be the case. Madam Chair, before I yield back, I would like to quickly congratulate Dr. Drel on being named Dean of Engineering at Stanford University. She'll be the first woman to serve in that role, and that is noteworthy and worthy of our congratulations. This is even more evidence that we have truly assembled some of the top minds in the field here today. Thank you again for holding this hearing, and I'm looking forward to learning more from our panel. And with that, I yield back.
I thank the to submit additional opening statements. Your statements will be added to the record. At this time, I would like to introduce our witnesses. Our first witness today is Dr. Steve Ritz, P5 Chair and Professor at the University of California at Santa Cruz. Dr. Ritz is also the Director of the Santa Cruz Institute for Particle Physics at the University of California. Previously, Dr. Ritz was a professor of physics at the University of Maryland, an astrophysicist at NASA's Goddard Space Flight Center as well. Dr. Ritz received his PhD in physics from the University of Wisconsin. We welcome you and warmly appreciate your attendance today. Our second witness is Dr. Persis. Is it Persis? That's a beautiful first name. Dr. Persis Drel, Director Emerita of the SLAC, National Accelerator Laboratory. Dr. Drel served as Director of SLAC from 2007 to 2012. Dr. Drel is also a professor of physics at Stanford. Previously, Dr. Drel was the Associate Director for the Research Division at SLAC. She has also served as Deputy Project Manager for the Fermi Gamma Ray Space Telescope. Dr. Drel received her PhD in atomic physics from the University of California. I understand you also were one of the conceivers of the notion of the P5, which I believe has worked extremely well, and we thank you for your foresight in organizing these issues. Next, I would like to introduce, oh good, Mr. Hultgren's here. I'm so pleased because he had asked to introduce today's third witness. So at this time, I would like to yield to the gentleman from Illinois, Mr. Hultgren, to introduce Dr. Rowe. No, excuse me. Dr. Locke here?
Yes.
Perfect.
You apologize for being a little bit late. I had to run by markup and financial services, but great to be with you today. Thank you all so much for being here. It really is my honor, Madam Chair, to introduce someone who's doing a great job and has become a very good friend. Our third witness today is Dr. Nigel Locke, Director of Fermi National Accelerator Laboratory. Previously, Dr. Locke served as the Director of Canada's National Laboratory for Particle and Nuclear Physics, TRIUMPH. He was also Professor of Physics and Astronomy at the University of British Columbia. Prior to his work at the Canadian Physics Laboratory, Dr. Locke served as a professor of physics at the University of Pennsylvania. Dr. Locke earned his PhD in physics from the Ohio State University. So glad you're here. Thank you, Dr. Locke, and thank you for your great work at Fermilab. I yield back. Thanks, Chairwoman.
Thank you, Mr. Hoagland. Our final witness today is Dr. Nathalie Rowe, Director of the Physics Division at Lawrence Berkeley National Laboratory. Dr. Rowe joined Lawrence Berkeley in 1989 as a kindergartner, apparently. No, it says as a postdoctoral fellow. I suppose those things can happen simultaneously, but it's impressive, Dr. Rowe, very impressive. She has a distinguished record of research and service to the Physics Division, the laboratory, and to the national high-energy physics community. Dr. Rowe has been an active participant in developing the strategic vision of the Physics Division and has been a member of its advisory committee since 2006. Dr. Rowe received her PhD in physics from Stanford University. As our witnesses should know, spoken testimony is limited to 5 minutes, after which members of the committee will have 5 minutes each to ask questions. Again, panel, we're delighted you're here. I now recognize Dr. Ritz for 5 minutes to present his testimony.
Very good. Thank you. Can you hear me? Yes. Chairman Lummis, Ranking Member Swalwell, members of the subcommittee, thank you for inviting me to this important hearing. Particle physicists have come together to make a recommended plan that is driven by the science and that meets tight fiscal constraints. The plan enables leadership by the United States, resolves key issues for the field, and envisions a continuous flow of exciting and important results while making essential investments in the future. HEPAP, the FACA panel advising the DOE and NSF, considered the report carefully and voted unanimously to approve it on May 22nd, 2014. As you know, particle physics explores the fundamental constituents of matter and energy, revealing profound connections underlying everything we see. The field is highly successful. There have been major discoveries recently that point the way forward, and since 2008, 3 Nobel Prizes related to particle physics were awarded. I'd just like to add here that one of the recent Nobel laureates, Saul Perlmutter, was a member of our panel. We very much appreciated that. Research in particle physics inspires young people to engage with science. Particle physics is global. Addressing the most compelling questions of the field is beyond the finances and technical expertise of any one nation or region. The U.S. and major players in other regions can together address the full breadth of the field's most urgent scientific questions if each hosts a unique world-class facility at home and partners in high-priority facilities hosted elsewhere. Strong foundations of international cooperation exist with the Large Hadron Collider, LHC, at CERN, serving as an example of a successful large international science project. Tough choices were required. Our panel understood that an important part of our job was to recommend ways for the U.S. to invest purposefully in areas that have the biggest impacts and that make the most efficient use of limited resources. The charge calls for planning under 2 specific budget scenarios with 10-year profiles reflecting current fiscal realities, as well as a third unconstrained scenario. We started with the science. A year-long community-wide study called SNOWMAS preceded the formation of P5. Based on this comprehensive work by the broad community, we identified 5 compelling lines of inquiry that show great promise for discovery over the next 10 to 20 years. These are the science drivers of the field. And they are: use the Higgs boson as a new tool for discovery, pursue the physics associated with neutrino mass, identify the new physics of dark matter, understand cosmic acceleration, dark energy inflation, and I assure you this inflation does not involve the consumer price index, as if you were wondering, and explore the unknown, new particles, interactions, and physical principles. I look forward to discussing these with you in more detail and why we're really so excited about them. The prioritization is in the selection and timing of the specific projects to address these science drivers. using an explicit set of selection criteria that we developed, we recommend some projects not be implemented and some existing efforts be reduced or terminated. Having made these choices, the field could move forward immediately with a prioritized and time-ordered recommended program, which is summarized in the report in Table 1 and includes the following features. The enormous physics potential of the LHC, which will be entering a new era with its planned upgrades, will be fully exploited. U.S. scientists continue to play very visible leadership roles, and the provided hardware would be designed and built here in the U.S. The U.S. would host the world-leading neutrino program with an optimized set of short and long baseline neutrino oscillation experiments. You'll hear more about that. The long-term focus of the program would be the Long Baseline Neutrino Facility, LBNF. The Proton Improvement Plan, PIP2, project at Fermilab would provide the world's most powerful neutrino beam. Large projects are ordered by peak construction time based on budget constraints, physics needs, and readiness criteria. This was an important thing the panel did. Several small and medium-sized projects in areas especially promising for near-term discoveries and in which the U.S. is in a strong leadership position would move forward under all budget scenarios. Another important project of this type, the Dark Energy Spectroscopic Instrument, DAISY, would also move forward except in the lowest budget scenario. Specific investments would be made in essential accelerator R&D and instrumentation R&D, and the interest expressed in Japan in hosting the International Linear Collider is an exciting development. Recommended participation by the U.S. in project construction depends on a number of factors, some of which are beyond the scope of P5. 6 significant changes in direction are recommended. Of these, I highlight here the first one, increase investment in construction of new facilities. In constrained budget scenarios, this will necessarily entail some judicious reductions in the research program. This represents a large commitment to building new experiments, which we see as essential. We titled our report, Building for Discovery. As detailed in the report, and as I hope we can discuss today, the bang for the buck of relatively small incremental investments in particle physics would be really big. The lowest budget scenario is precarious. It approaches the point beyond which hosting a large project in the U.S. would not be possible while maintaining the other elements necessary for mission success. Without the capability to host a large project, the U.S. would lose its position as a global leader in this field, and the international relationships that have been so productive would be fundamentally altered. The broader impacts of particle physics research are many. These are summarized in Section 4 of the report. Topics include material science, medical imaging and therapy, computing, neuroscience, and bringing to life the earliest audio recordings. There was a continuous effort on many fronts throughout the P5 process to maintain direct community involvement. I see my time has run short, so I'd be happy to discuss that further with you in questions. It was a very important process, and the way in which we work, I think, really resulted in the best possible plan for the field. In conclusion, the P5 report offers important opportunities for U.S. investment in science, prioritized under tightly constrained budget scenarios in the charge. Wondrous projects that address profound questions, inspire and invigorate far beyond their specific fields, and they lay the foundations for next century technologies we can only begin to imagine. Historic opportunities await us, enabled by decades of hard work and support. The U.S. particle physics community is ready to move forward. Thank you for your support of U.S. science and for the opportunity to be here today. I look forward to hearing your thoughts and answering your questions.
Thank you, Dr. Ritz. I now recognize Dr. Drel to present her testimony.
Chairman Loomis, Ranking Member Swalwell, members and staff of the subcommittee, I too am very pleased to be here today to provide my perspective on the future of particle physics in light of the new P5 report. It is a particular pleasure for me to participate in these hearings. 12 years ago, I was part of the HEPAP subpanel that recommended the creation of P5. We believed that such a prioritization process would be essential in ensuring that we judiciously use the available resources in our field, both human and financial, to pursue a balanced, diverse, and exciting program. It is not possible to pursue all of the scientific opportunities we see before us. We must choose wisely. In my opinion, this recent P5 report does an outstanding job of setting the path forward for U.S. particle physics. Fully recognizing that resources are constrained, the report sets forth a staged plan focusing on the most compelling science, building on U.S. strengths across the field, ensuring that the U.S. retains a leadership role in this important area of research. Before discussing the report, it helps to remember why having a healthy particle physics program is important for our nation. I will start with the science. Particle physics asks very basic and fundamental questions about the world we live in. It is incumbent on us to pursue the answers to those questions, as has every great society that has preceded us for millennia. In addition, the fundamental nature of these questions draws interest to science generally. Just look at the excitement over the discovery of the Higgs. And while many factors go into an individual's decision to pursue a career in science, the idea of big, fundamental questions out there just waiting to be answered is certainly one enticement. Finally, particle physics is an essential part of the fabric of the physical sciences in the United States. It contributes broadly to other disciplines and benefits enormously from research in other fields. A vivid illustration of the interplay between different scientific fields comes from SLAC National Accelerator Lab, where I was the director from 2007 to 2012. SLAC was born as a particle physics laboratory. We turned off our last accelerator for particle physics in 2008. In 2009, we turned on the world's first X-ray free electron laser, the LINAC coherent light source. The LCLS is a tool for chemistry, for biology, for material science, for condensed matter physics. It's not a tool for particle physics. However, its rapid early success relied on years of research and development in particle physics aimed at making precision-controlled beams of electrons for future linear colliders. The challenge we've been facing for some time now is how to craft a healthy particle physics program in the U.S. with constrained resources and in an increasingly international environment. The P5 subpanel has done an outstanding job of charting our course. They started, as Dr. Ritz said, with the science. To be successful, we need to focus on and prioritize the opportunities that give us the most transformational scientific advances and attract the best talent. Following a year-long process of engaging the community, P5 articulated 5 intertwined science drivers for the field, and then developed criteria for their prioritization process and evaluated the projects against those criteria to craft the program for the future. The P5 process engaged the entire community, both laboratories and the university community. The transparency and inclusivity of the process were phenomenal and exceptionally well done. The community is deeply in debt to the leadership shown by Dr. Ritz. The plan P5 crafted reflects the voices, priorities, and thoughts of many in our community. It is the reason the community can stand behind this plan. In ending, I would like to note that the field of particle physics in the U.S. and in the world is changing dramatically. We used to define ourselves solely in terms of our primary accelerator tools. But to quote the former White House science advisor Jack Marburger, opportunities have emerged for discovery about the fundamental nature of the universe that we never expected, and technology places those discoveries within our reach. Going forward, we must have a program that allows us to focus efforts across a broad variety of tools to realize the new scientific opportunities. That includes observatories in space, telescopes on mountains, sensitive detectors in deep caves under the Earth, in addition to our traditional accelerator tools. The plan outlined by P5 and supported by the particle physics community is a realistic, executable roadmap for a new era, and it will enable a future of discovery that is every bit as exciting as our past. It was hard, but the results are worth the effort. This roadmap will allow the field to move forward and to deliver success. Thank you for the opportunity to share my views with you today.
Thank you, Dr. Drel. And now the chair recognizes Dr. Locke here for your opening statement.
Thank you. Good morning, Chair Lummis, Ranking Member Swalwell, Congressman Holgren, and other members. The P5 report lays out a bright future for particle physics community, and that Fermilab strongly supports the recommendations of the P5 report, and it has embraced its role in implementing the strategic vision for the field. If implemented, the report should maintain and reinvigorate U.S. leadership in particle physics. For the benefit of the ranking member, Fermilab is located 42 miles west of Chicago in Batavia, Illinois. It is a 68,000 I wish it was, 6,800-acre laboratory, 1,700 employees, 2,100 users. It has the largest accelerator complex in the U.S. and delivers the most intense beams of neutrinos, not only at Fermilab, but also to Minnesota. So the beams themselves travel through the Earth, which is one of the more interesting properties of neutrinos, that they travel through just about anything. Fermilab is largely open to the public and is the home of a small bison herd, better known as buffalo. And Fermilab is managed by the Fermilab Research Alliance, a partnership between the University of Chicago and the URA, an association of 88 universities. 40,000 K through 12 students participated in activities at Fermilab last year. 8,000 visitors took tours or dropped into the Laterman Science Center. And over 1,000 college and university students are involved in on-site programs and internships. So to put things in a little bit of context, the U.S. has been amongst the leaders in particle physics for the last several decades. Fermilab operated the highest energy collider in the world. The U.S. pioneered superconducting magnet technology and built the first large superconducting accelerator, the Tevatron, which was 4 miles in circumference. Over 1,000 graduate students received PhDs, and over 1,000 scientific papers were published from that program. The discovery of the top quark, as you heard from the chair, was the crowning achievement, the heaviest fundamental particle ever observed. Today, the Large Hadron Collider is the highest energy in the world. So what's next for the U.S.? P5 has endorsed a portfolio of projects. I will comment on 3, the LHC, the ILC, and neutrinos, LB and F. Our goal is to have one optimal accelerator-based neutrino program in the world. Okay. And not 3 suboptimal facilities. So strictly limited by physical and human resources and not by the ambitions of the scientists. We're trying to collect everybody together into one single program. P5 recommends we fully exploit the Large Hadron Collider. The program has tremendous discovery potential, and I think the anticipation in our community is really something when you ask people about what they expect to come out of the program in the next few years. It's going to be the highest energy again. They're stepping up the energy, and everybody's quite excited about that. So the existing science, as you've mentioned, attracts some of the brightest students into physics. U.S. technology contribution to the LHC in the future is critical. The high field magnet technology has now evolved to yet a new type of conductor, niobium-310, and the U.S. is the only place that makes that. That's been done with a collaboration by DOE Office of Science Labs, Brookhaven, Lawrence Berkeley Lab, and Fermilab. The P5 report is supportive of U.S. involvement in the International Linear Collider. The 20-mile-long accelerator has been designed by a global team over the last decade, and Japan is now seriously considering hosting the machine. The U.S. and Fermilab is well suited to contribute technically to the machine. In fact, it's hard to imagine Japan being able to proceed without our partnership. It's truly a huge undertaking and certainly worthy of a global project. Our community has decided that neutrinos are where the action is. You have 100 billion neutrinos going through your thumbnail per second as you sit here in this room. The particle indeed is very mysterious and continues to surprise physicists after every major measurement. It has to be important. P5 envisioned a program of experiments over short distances and one over a long distance all the way to the Sanford Underground Research Facility in Leeds, South Dakota. The old Homestake mine where Ray Davis, my office mate at the University of Pennsylvania, did his work to earn the Nobel Prize for detecting neutrinos from the sun. For LB&F, there's a near detector and a far detector, one at Fermilab and one in South Dakota. The detector would sit about a mile underground and be, at least in the present configuration, 40,000 tons of liquid argon, or liquid air, if you like. The impact of fundamental physics is significant, too. Fermilab is making a concerted effort to commercialize its technology to help create jobs for Americans, build industries, and contribute to society. Today, we see small, portable, high-power accelerators as having the potential to have major impact on numerous industries, such as microelectronics, transportation, and the natural gas industry. I'm happy to expand upon these in our discussions. Finally, let me say again that the P5 report lays out a bright future for the U.S. particle physics community in a global context. The report has made clear choices, and Fermilab is beginning to implement these choices along with our colleagues at OHAP in the Department of Energy.
Thank you, Dr. Locke here. And we don't know why those buzzers go off when they do, but we appreciate your unflappability with regard to that. I now recognize Dr. Rowe to present her testimony.
Thank you, Chairman Lummis, Ranking Member Swalwell, distinguished members of the subcommittee, and thank you for inviting me to participate in this important hearing. I completed my graduate studies in particle physics 25 years ago at SLAC. My thesis experiment had roughly a dozen scientists, cost less than $1 million, and it was built, commissioned, took data, and published its main results all during my time as a grad student. Today, the Large Hadron Collider is a multi-billion-dollar machine. The design of the LHC began over 20 years ago, and each of the 4 experiments has several thousand physicists. With suitable upgrades, the LHC will likely continue for another 20 years. This increase in scale, in size, in dollars, in time, and in human capital is necessary to extend our reach to higher energies and higher intensities. Although I've witnessed these dramatic changes in our field, small and intermediate scale projects, such as the one I participated in at Stanford, still have tremendous potential to make groundbreaking discoveries. This was recognized in the P5 report, which stressed the value of a balanced portfolio. And my goal today is to explain this recommendation of P5 and provide a few key examples of small and medium-sized projects with big potential. As evidenced by my personal experience, these smaller projects provide excellent training for students and postdocs. Smaller experiments can go after blue sky ideas, they can be nimble, and take risks with the potential to shake up the field. A prime example of what can come out of a small project is a project started in the early 1990s called the Supernova Cosmology Project, led by a young physicist named Saul Perlmutter. Saul's plan was to use supernovae, or exploding stars, to measure the rate at which gravity was causing the expansion of the universe to slow down. In what is now a famous result, Saul and his team had measured enough supernovae by 1998 to conclude that the expansion of the universe was in fact accelerating. The expansion was going faster and faster. In other words, some force counteracting gravity is at work in the universe. We call it dark energy because we just don't know what it is. The result was completely unexpected, and it was a dramatic event for the physics community. This work, this small project, ultimately led to a Nobel Prize. Saul's discovery has attracted the attention of scientists all over the world and inspired a new generation of students to study physics. Out of this small experiment, a whole new field of research has been created, and our concept of the universe has been fundamentally changed forever. Obviously, the return on the federal government's investment in this case was huge. And dark energy remains one of the biggest unanswered questions in fundamental physics today. Much more precise data is needed to figure out which of the many proposed theories is correct. The Dark Energy Spectroscopic Instrument, or DESI, is one of the small-scale projects recommended by P5 that could tackle this problem. DESI reuses an existing telescope at Kitt Peak, Arizona, and installs a new instrument and dedicates it to a wide area survey of the universe. DESI will bring a new level of precision to the study of dark energy and could be built for about $40 million over 4 years. DESI would enable the U.S. to remain a leader in dark energy research into the next decade. P5 also recommended that the U.S. should remain a leader in the search for dark matter. Dark matter outweighs normal matter by about 6 to 1, and without it, the stars in our galaxy would fly off into space. A deep underground site to carry out this type of dark matter search already exists in the U.S. in the state of South Dakota. It is called the Sanford Underground Research Facility, or SURF. SURF hosts the world's current most sensitive dark matter experiment, and it could provide a home for one of the next generation dark matter experiments that P5 recommended. SURF is also where the neutrino detectors for the Long Baseline Neutrino Facility that Nigel discussed will be located. Particle physics has come very far in the past century, finally discovering the long-sought Higgs boson. only to realize that we do not understand what makes up 95% of the universe, the mysteries that we call dark matter and dark energy. This is both humbling and exciting. P5 has recommended a carefully selected set of interlocking experiments, including a number of small to medium-sized projects in this cosmic frontier. This program is optimized to achieve the most cost-effective approach in our quest to further understand the nature of matter, energy, space, and time. Thank you for your attention. I'm very happy to answer any questions you may have.
I thank the witnesses for being available for questioning today and for your really exciting testimony. I remind our members that committee rules limit questioning to 5 minutes, and so at this point I will open the round of questioning. So I recognize myself for 5 minutes. Now, in your report, the P5 recommends that the budget fraction for construction increase to 20 to 25%, and I understand right now it's around 16. So my first question is for you, Dr. Ritz. How did the P5 come to this determination, and what is the significance of the likely outcome if DOE adopts this recommendation?
Yeah, thanks for the question. This was one of the tough issues. In a constrained budget scenario where there's a top-line number, if you increase the fraction devoted to projects, that means it comes from some other place. And in this case, the other parts of the budget are in research, in the research program, and operations. And in the planning, there has been recently a reduction in the research program, and we endorsed that and said that at least in the leanest budget scenario, that was going to be necessary. That the program that you get if you don't devote the necessary resources for building things was just not going to get us where we need. And that's why we called the report Building for Discovery. So this was a very tough choice, something that was discussed quite a bit. There are recommendations in the report about how to manage that those expenditures judiciously, particularly for the research program.
So this recommendation has implications for the colleagues at the table. So I want to ask Dr. Locke here and then Dr. Rowe this question. How will the P5's recommendation to increase the budget for construction affect operations and research at your respective labs?
Good question. So first of all, I will say that we're in agreement with the idea that you have to really build for the future. So as I tried to mention, the context of where we are now is that we've just come off being the leaders in the world in particle physics, having the highest energy machine, and now the question is what's for the future. And so you have to build something, and in order to do that, that comes through the project funding line. So now the issue is how do you shrink the research program and how do you shrink the operations? And the answer is carefully. I think we have to do that. We know we have to do that. But in terms of shifting workforce and so on, we'll be moving people that would normally work on operations and move them into these research projects, which actually for a lot of engineers and scientists is a nice shift.
Dr. Rowe?
I would just mention that we have already seen a contraction of our research program. I believe that all of the national labs that have HEP programs have already had reductions in force. And it's been a painful process, but one that we recognize is necessary in order to increase our investment in exciting projects that will inspire young scientists and keep the U.S. at the forefront of particle physics. So it's a sacrifice that we've already been making and that we realize may have to continue.
Dr. Drel, I do have a question for you as well. Given your experience in this field, how do you view this specific recommendation by the P5, and is it worth the trade-off?
I also agree with the others that it absolutely is worth the trade-off, that it is painful for today, but it is what makes the future possible. and therefore I completely support it.
Have any of you had experience with leveraging the construction component by having universities or states, in the event of its expansion in the United States, contribute to this because of the opportunities it provides for economic development, for the recruitment of world-class intellectual prowess to their states, and all that means for a community?
Yes, very much. That's a great question. As a university member, let me just say that universities and laboratories work in partnership wonderfully together. Having students, postdocs, resident universities, which still have some infrastructure for producing detectors at experiments, is a wonderful way. It's also an extremely efficient way of building these experiments. So yes, it is an extremely important part of the field. It has been a challenge to maintain the infrastructure at universities with the overall shrinking capability, but it is core to our field. I'm sure Nigel, Nathalie would agree.
I thank you. My time has expired, and now I yield to the ranking member, Mr. Swalwell.
Thank you, Chair, and thank you to the witnesses and Dr. Locke here. Thank you for telling me about Fermilab. You have a faithful advocate in Congressman Holtgren, and I am now assured that you were put on this panel for more reasons than just separating the Berkeley and Stanford witnesses, who at home would be at odds with each other. Dr. Rowe, I understand that you and your colleagues had to make a number of tough decisions under a difficult set of budget trajectories, and I commend you for rising to this challenge so that members of Congress without particle physics degrees don't have to make these decisions without your guidance. And I am, however, concerned about the consequences of the lowest budget scenario that you were required to consider. And with that in mind, I wanted to talk a little bit about DESI and why that's so important to improving our understanding of dark energy. And if you could also talk a little bit about what the sense of impacts on the U.S. physics community would be if this experiment was not allowed to move forward.
Well, thank you very much for that question, Representative Swalwell. DESI is really a unique experiment in that it can make these very precise measurements of dark energy extending back billions of years in cosmic time, but at a cost that is very modest, considering that its reach can rival expensive space mission capabilities. And the key is to recycle this existing telescope that the NSF has at Kitt Peak in Arizona that they were planning to retire. So we're making use of an existing facility, outfitting it with a modern robotic fiber-fed spectrograph that we can measure 5,000 galaxies at a time with. And there's a lot of excitement around this project, and it would certainly send a very discouraging message to the many young scientists who have already voted with their feet to join this collaboration. They're excited about the science, eager to take on major roles and responsibilities. And also, if we can't proceed with DESI, it would send a negative message to our many collaborators from 10 countries who have indicated that they wish to invest here in this experiment. And they may decide to try to do this experiment themselves in Europe or Asia rather than wait for us to commit if we can't do it.
And Dr. Rowe, speaking of Europe or Asia, if DESI is funded and moves forward as a project, what will it be able to accomplish that cannot be accomplished or will not be accomplished by LSST or by the European dark energy missions and experiments that are expected?
Well, DESI is very complementary to these other missions, as was called out in a community report on dark energy that the Department of Energy asked for 2 years ago. Basically, whereas DESI uses spectroscopic techniques measuring the spectrum of galaxies, LSST uses imaging techniques, taking pictures of galaxies. And by doing these different approaches, they can constrain dark energy with different and complementary methods. Because it's such an unexpected phenomenon, we feel that we need confirmation from multiple techniques to really understand what's going on. So they really fit together in a planned program.
Great. Thank you, Dr. Rowe. And Dr. Drel, as you mentioned in your testimony, this is not your first P5 rodeo. so to speak. You were pivotal in the creation of the first P5, and I was wondering if, thinking broader, you could can you envision this process that the P5 undertook? Can it and should it be applied to other areas of research that require long-term prioritization of projects under challenging budget scenarios? And if so, any examples?
So actually other fields use processes that they're not called P5, but they have a similar outcome and are tuned to the specific circumstances of those fields. For
How about fields that aren't using it that you think would benefit if they took this process?
I think most of the fields that I can think of, astronomy and astrophysics with its decadal survey, X-ray science with the BSAC subpanels, nuclear physics, they have a very good process. The fields that I'm aware of that really need to do this have their ways of doing it. It's, I think, in some ways hardest in high-energy physics because of the huge opportunity costs of our projects. They are so long that you make a decision now and it really constrains the program many, many years in the future. And it was that additional element of opportunity costs we felt wasn't being taken into account in 2002. But I think actually we, in the P5 process, learned from how other fields do it. And in the way of science, they will learn from how this was done as they go forward in their planning.
Great. Thank you, and I yield back the balance of my time.
I thank the gentleman, and when I was in college, I studied the biological sciences and found myself with a considerable amount of physical sciences deficit in my own intellectual capabilities. So I marvel at your capabilities intellectually and the excitement that you bring. But we do have one member of this committee that is at your level. And I recognize him now, the gentleman from Kentucky, Mr. Massey.
I'm definitely not at your level, but let's manage expectations, Cynthia. But please bring it down to our level a little bit here. Can you explain, any of you, the significance of the Higgs boson and why congressmen and congresswomen should be interested in that discovery? And also the location of that discovery. Dr. Ritz.
Sure, I'd be happy to do that. It's really an amazing time in physics, and let me try, rather than try to describe electroweak symmetry breaking and all the technical terms people try to explain why, let me step back a minute and just try to give you a sense of why we're so excited about it. And it really reminds me of a story when I was a graduate student and I earned my keep by being a TA. We had intro physics labs. I actually really enjoyed teaching the biological science students, actually, at Santa Cruz. It's great. And there was one of these labs that you probably remember. It wasn't all that exciting. It involved a plunger and a piston and a spring, kind of like a pinball thing, you know. And I said, well, you know what, why don't you take that and aim the thing at some angle and calculate where the thing's going to land. Put a piece of paper there. And, you know, one of the students did it. And he, you know, thank goodness, it hit spot on. And he was just so excited about that. I'll never forget this, that he just wrote in his laboratory book in all caps, Newton's laws allowed me to predict where this was going to land. Physics really works. He was just so excited. So fast forward from Newton's time to the late 1800s, when people studying electricity and magnetism realized they're actually two different aspects of the same thing. Okay? Electricity and magnetism are actually unified forces. And that became the basis of all the technology that we enjoy today. Now come to our era, there's another force. There aren't that many forces. That's what's amazing. There's another force that can be unified yet with electricity and magnetism. That's called the weak force. So here's the really interesting thing, and that's related to that student back in Wisconsin. You take all of these phenomena that we see in our experiments, and you can write down a theory that's really abstract, and it involves all these terms that take a long time to explain. It's really beautiful stuff. It's fantastic. You look at that and you say, this all works if this other phenomenon that we never thought to look at, that we never in a million years would think to do, and it took us 30 years or 40 years of experiment to find, We built the machines, and we did it, and it was there. Okay, science doesn't really get any better than that. We understand it at a profound level. Now, what the significance of the Higgs is going to be, it's just too soon to tell. It's a fantastic new discovery. It's a entirely new kind of particle, and as you can tell, I think we're extremely excited about it. Now, you asked about where. So it was discovered at the Large Hadron Collider facility at CERN. The U.S., I believe, should be very proud of our role in that discovery. We had leadership in the 2 experiments that discovered it. It was our hardware that helped to make it possible. And for the next step, these high luminosity upgrades, the upgrade to the machine, this is absolutely the best game in town. It won't happen. It can't happen without our know-how, as Nigel said, and it truly is a world discovery.
So for everybody here, CERN is in Switzerland? Okay.
Yeah, actually the particles cross the border between France and Switzerland.
And probably
it's an open border.
Are escaping into the universe too, right? So let me just play devil's advocate here. And
sure.
I assure you this is being devil's advocate. Why can't the U.S. just kind of sit back and wait for the rest of the discoveries to happen in Switzerland and let our international partners just ride on their coattails?
Sorry, Nigel, would you like to answer that? Sure.
Sure. I think the main issue here is the technology associated with that, from my standpoint. So as I mentioned before, CERN relies on the U.S. for the next phase of the machine to be building the high field magnets, which give it the high luminosity, which allows you to do the new physics. We keep that technology. We own that technology. And so that's the technology that I think is going to be important when we try and apply it to the commercial side of things. So you don't lose any of that. At the same time, your scientists are working at the absolute forefront of the field, and they come back excited about what they've learned. The students come back excited about what they've learned. They're not all going to stay in the field. In fact, roughly half of them go into business and other areas of that they pursue in their careers.
Occasionally, engineers get lost in Congress too.
They do, but I think that's so there's benefits both on the people side and on the technology side, and it works both ways actually.
Thank you very much. My time's expired.
When I first met my colleague, Mr. Massey, who is a graduate of MIT and holds dozens of patents, I asked him, tell me something you hold a patent in. And he said, well, I hold a patent in how one can feel non-matter. And I said to him, how did you know that would be of any significance? And he said, I didn't, and I still don't. And someday somebody will make that next step. And in some ways, that's what you're doing. That's what's so exciting and pioneering about it.
Well, one thing's for certain. I used to work in virtual reality, and I'm back in virtual reality.
The chair completely understands that statement. I now recognize the gentleman from Illinois, Mr. Lipinski.
Thank you, Madam Chair. Thank you for holding this hearing. I try to understand particle physics, but I'm only an engineer, so I don't quite reach those, have a hard time reaching those levels. But very happy, good to see you, Dr. Drel, and I understand you're the new chair of Dean of Engineering at Stanford, where I got a engineering degree out there, so I was very happy to hear that, and good to see you, Dr. Locke here. I think Representative Holmgren will be probably asking questions next on this. I know it's a great facility we have there in Illinois, out in his district. But I wanted to, first of all, talk a little bit more generally. I was very happy to get connected with David Kaplan and Mark Levinson when they were first really starting on Particle Fever, the movie. And I highly recommend the movie. I was able to. I gave the introduction here in Washington for the premiere of the movie. When the weekend it premiered in Chicago, I went to the movie, and David was there and answered questions afterwards. And I never expected to see the kind of excitement that came out of that movie for the audiences. But I never expected that anyone could put together a movie to make particle physics really interesting and somewhat understandable. It helped me better understand after spending many, many hours over the years talking about particle physics. The movie did a great job of helping me to understand, okay, what we're talking about. Help an engineer try to understand what we're talking about with particle physics. But it's great to see, and I said the way the movie ended with the discovery of the Higgs boson, but still leaving sort of the cliffhanger of, okay, what does this mean now? I said it was just a perfect setup for the sequel. But and we're all waiting to see where we go from here. But I wanted to ask Dr. Locke here about the Illinois Accelerated Research Center. I know the Department of Energy and the state of Illinois are in the partnership to build that, and once completed, the center is going to conduct research and help establish partnerships between the scientific and business communities to solve problems related to energy, the environment, medicine, and national security. I think that this is something where we see in our roles here, it's hard sometimes to make the case for basic research and funding of basic research, and people want to see results. What does this mean to us? As Dr. Massey was getting at there, a lot of times you don't know for a long time, but we see it somewhere. But when we're talking about the center, can you say a few words about what you hope you'll be able to do in terms of economic development and in job growth?
Thanks for the question. The Illinois Accelerated Research Center is the sort of the focus of Fermilab's attempt to commercialize the technology associated with particle physics, and in particular accelerators. So maybe I'll give you an Illinois example, and you can apply it to the rest of the country. So, for example, high-power electron accelerators can be used to polymerize hydrocarbons, which means the bonds can be rearranged in a way that changes the texture and the behavior of the material. One example is radial tires are treated with electron beams to make them harder. So obviously that's a good thing. So what we're looking at now, for example, is looking at asphalt. So asphalt is a combination of gravel and bitumen, and we're looking at changing the chemical structure of the bitumen so that the asphalt is harder and lasts longer. $80 billion of money goes into paving roads in the United States. So if you can make a road last an extra year, it's a big deal. So we envision being able to treat the asphalt as you lay the pavement down with portable accelerators. You've seen this in the highways where they lay the asphalt and you try and stay away from it because it's a mess in terms of traffic. But we can imagine mounting small accelerators on the back of that vehicle and hardening the road as you lay it down. And so we've started that kind of research. That's just one of the examples we're looking at. But there's a number of other ones I could give you afterwards if you like.
I appreciate that, and it's something as an engineer and a member of the Transportation Committee I can appreciate it and understand. So thank you. I'll yield back.
As you can see, our members from Illinois are rightly proud of what is occurring at Fermi, and I now turn to one of them, the gentleman from Illinois.
Thank you. Madam Chair, first of all, I ask unanimous consent to enter into the record a letter from the American Physical Society supporting the P5 process and its plan for the future of particle physics in the United States.
So moved.
Well, thank you, Chairwoman Lummis, so much. Thank you all, to all of our witnesses for being here today. I know sometimes my colleagues do get tired of me talking incessantly about Fermilab, so it's great to have some people here who actually know what's going on there before the subcommittee and the great things that you're doing in this very important field. Since the shutdown of the Tevatron, I know how hard the community has been working to find the next frontier we will be embarking upon. We've heard the Secretary talk about the community getting on board for a plan, and that's why I'm so grateful for the work of P5 that you did to put forward a responsible plan taking into account the budget constraints for this vision, which ensures projects that could be funded and realistically executed. I'd like to thank Dr. Ritz and everyone involved for their hard work that they put into this. From everything I hear, the community has accepted this plan and is as appreciative for it as I am as well. Dr. Locke here, at this time there are only 6 universities offering graduate programs to train accelerator scientists and technologists here in the United States. This is often a field that is self-selected, and we need to maintain a leadership role just to maintain the capabilities and expertise we already have. I wondered if you could explain the PIP2 upgrades, what they'll make available to Fermilab and to the community as a whole. Besides just the long-base neutrino experiment, what other experiments will this technology and R&D allow the community to do?
Thanks for that. The PIP2 project, Proton Improvement Plan at Fermilab, is the one I'm personally excited about because it really goes to the heart of what our field is trying to emphasize, which is accelerator research. The technology associated with it we refer to as superconducting radio frequency technology. We are pushing the envelope in what you can do with that. It has applications in other fields. It has applications in commercialization. And because it is new and because it is a challenging project to build, it will allow us to stay at the cutting edge of accelerator research over the next decade and provide the most powerful neutrino beams in the world. So again, that will be our competitive advantage on the science side. It's also a great place for training students. And I agree, there is a shortage of accelerator physicists. The schools that do offer accelerator programs are the top schools in the country. We're working with Northern Illinois University to create a program there. The new president, Doug Baker, is very committed to doing that. And so I see that there's numerous opportunities we have to impact our field on that.
And I appreciate that. And I think that is such an important story, again, for all of us to be reminded of, is the great cooperation that's going on there, but also preparation that needs to happen. Dr. Locke and Dr. Ritz, since the report has been published, there have been some questions from the community as to whether LBNE will need to be completely reworked to create the international facility the report is pushing for. Wondered, is this the case? And if not, how will LBNE be rolled into LBNF? Should our international partners have faith that our previous work is relevant and continued project engineering and design work is worthwhile?
Well, let me start and then hand it over to Nigel. The answer is yes. I think they should have faith. I think the report is actually a resounding endorsement of this science. It's, in a sense, to quote President Reagan, throw deep, that this is the community spoke very clearly at the Snowmass meeting, and also our international colleagues in their expression of interest have said they really want this to be a capable experiment. So this is something that's going to take the world neutrino community to come together to make happen. And we are in an excellent position in the United States to host this facility, both with Fermilab and the Sanford Underground Research Facility. And let me hand this over to Nigel, who is also, of course, working on the implementation.
Yeah, I think this is one of the more challenging aspects of the P5 report for Fermilab and for the community. I think it is necessary to, in order to have the absolute optimal experiment put together, that you have all your friends there, you invite their ideas. And so we're going through a process now of where we're asking whether the international community can see themselves being engaged in what we've started. We think we've done a great job so far and made tremendous progress, and I see that the P5 report just gives us more momentum because they see us having success, not only success in technical success, but also in terms of getting our community behind us. So I'm very confident that we're going to see Europe get on board. Already CERN has said they want to be part of this. The UK and Italy have said they want to be part of this. Brazil has said they want to be part of this. So I see this as just, it's coming together now because I think the P5 report has just made us look more serious about what we're doing.
Well, again, my time has expired, but I do want to just thank you all so much. It's been a challenging couple of years, and this is an exciting time. I feel like we are right there, and you all have been such a key part of that. So thank you. We want to help. We want to get this message out to our colleagues of how important this is right now. So, Chair, thank you for holding this hearing, and I yield back.
I thank the gentleman, and before I recognize the gentleman from Texas, I want to alert our panel as to the plan here. We would love to have a second round of questioning if you are available. I will be turning the chair over to the gentleman from Illinois, Mr. Hultgren, and Mr. Lipinski of Illinois will assume the ranking member chair. Mr. Swalwell and I are going to step out and discuss the markup of the authorizing legislation that includes funding for high energy physics. So please excuse us as we have a sidebar in the back room. And I now thank you again for being here. I do recognize the gentleman from Texas, Mr. Vesey, and turn the chair over to Mr. Hultgren.
Thank you, Madam Chair. I did want to have a question about international research projects and wanted to direct my question to Dr. Locke here. I know that you're familiar with the ITER, which is being built in France and will be the first large-scale magnetic fusion facility in the world to produce net power. As has been mentioned multiple times, the LHC is under the Franco-Swiss border near Geneva, and Japan is bidding to host the International Linear Collider. Some may consider the fact that all of these next-generation major research facilities are being built in places outside the U.S. as evidence that we're losing our global leadership in research and innovation, and was wondering what you think about those concerns that have been expressed.
Thanks for the easy question. I think the situation is changing, and the global situation is changing with very large projects. And that's why I think it's so critical that the U.S. host its own large project. And we're seeing the P5 report is putting forward the idea that we would host a neutrino project. These are very different from, let's say, the ITER project, which is perhaps an example you want to stay away from in terms of challenges. It's had management challenges. It's had cost challenges. I usually draw your attention to our collaboration with CERN, which has been so successful that the project itself was capped. We delivered, the U.S. delivered what it needed to, everybody else did. It was done on time, on schedule, had tremendous success, as you know, with the Higgs boson. So I believe our field actually knows how to do international projects. We've demonstrated that. And so I don't have the same concerns that maybe people who want to put ITER and hosting a science project in the same sentence. They're quite different.
Well, how would we benefit? Like, how would the United States benefit? And I know Dr. Rowe wants to answer that, and she can answer that and jump right on into this too. How does the U.S. benefit from these international research projects, even if they're being conducted overseas? I think any of the panelists, Dr. Rowe, if you want to answer, go back to that and then answer that as well too.
Thank you. Thank you for the question. I think we do benefit by participating in international projects in many ways because our scientists, our engineers, our students contribute. We develop new ideas, we develop technologies, and we benefit our local economy by building things that are then installed overseas. But we don't want all of the leading particle physics projects to be overseas. If we do, we're likely to witness a brain drain where many of the most talented young scientists that are trained in the U.S. will pursue the better opportunities abroad. And we've long benefited from the influx of the best and the brightest coming here to pursue an education and the research opportunities that we offer. And a reversal of this trend, I think, would be very, very bad for the United States.
Thank you.
I completely agree with her answer. I think the issue is an exchange, And I believe that, as I said, that we should be hosting a project, but we also benefit by going abroad. And as I mentioned earlier, our technology most of the time is developed in this country, stays in the country, is used for our own purposes, and yet we benefit from working with the best and the brightest around the world in these projects.
Thank you. I yield to Beck Matan.
Thank you. We will now move to second round of questions, and I will yield to myself for 5 minutes. First question in the second round here addressed to Dr. Locke and Dr. Drel. I wonder, can you both explain the collaboration between high energy physics and other programs in DOE, especially basic energy sciences, and specifically drawing attention to LC-LS2 upgrades? How did this process work, and what continued R&D work is necessary in HEP to complete these kinds of upgrades and build other new light sources? Also, while HEP is the steward of accelerator R&D, will it always be work in HEP that drives this technology?
Let me start, and then maybe Nigel will complete. From the SLAC perspective, we have this magnificent opportunity to build LCLS2, building on fabulous science with LCLS. As you know, LCLS2 will involve a superconducting electron accelerator. We have no expertise in building superconducting electron accelerators at SLAC, but it is the way the system works in the DOE that the laboratories have competencies that are very often unique to those laboratories, and we help and support each other. This has gone on for some time, and for the LCLS2, we reached out to Fermilab and to Jefferson Lab and to Cornell, who are the world-leading experts in this technology, and they will then help us and build that for us. I would like to say that this is a remarkably efficient process. It means that rather than having duplicative competencies at different labs, we instead use our unique expertise to support each other. And it is going extremely well in the case of LCLS2. SLAC could not on its own build that facility without the help of our partners, and we appreciate that they prioritize it extremely highly, and it benefits science broadly in the nation, and that is really our goal.
Yeah, I would second that, and I will give you another example. So the P5 report talked about the cosmic microwave background as a new area that high energy physics would get involved in, and that also is a collaboration of various laboratories bringing different expertise to the table. So again, SLAC, Berkeley, Argonne, Fermilab work together to develop a chip, to mount chips, and each lab plays a different role, working with the broader university community at the same time. So I think we all know what we do well and what we don't do, and I think the idea that the labs work together makes tremendous sense to me, and I'm seeing that more and more all the time, and I know the Secretary is very much a big fan of doing that, and so we're doing it, and it's quite successful.
Good. I do think it's an important message for members of Congress to understand and to see, again, this ecosystem of how it works. We understand oftentimes our own labs, but don't understand how the working together, how important that is, and the ripple benefits across education, but also into the private sector as well. So I think it's great. Thank you. Dr. Ritz and also Dr. Locke, you're going back to your work with glass. You seem to be in a unique position to discuss how work in high energy physics is also affecting what we observe in outer space, whether it be dark matter, dark energy, or inflation. Can you talk about the expertise HEP will bring to the table for the next generation of space observatories and experiments such as LSST, which was also a top priority of the decadal survey? Also, what does neutrino science have to contribute to the understanding of the Big Bang and supernovas?
Oh, so much there. Great. Thank you. Yeah, so of course science doesn't know about all these different stovepipes that we invent just so that we can get our work done. And there are areas that fall between, there are really important aspects of science and great opportunities that fall between fields. And it's extremely important that they get done. Our report addresses that, as did the decadal survey that you mentioned, that by combining forces and doing the funding in a way that, in a multidisciplinary, multi-agency sort of way, that that matches the science output and the science yield that benefit each of the different disciplines, we think this is a great way to go, and it makes a big difference. Particle physicists are really great at building large-scale, highly integrated systems, large numbers of channels, very precise measurements, very careful attention to errors, great detail to pull out the physics. Okay, and combining that with the expertise of our astronomer friends and colleagues, if you're going to use the universe as a laboratory and make observations, you better talk very carefully and directly and collaborate with people who understand astronomy and astrophysics, that by working together you can pull out new information. So that's extremely important and extremely interesting. Neutrinos are a great example of a particle that just don't know which science discipline they belong to. There's particle physics, there's nuclear physics. Each play really important roles, and we work really well together on this, actually. You'd be surprised, but as Nigel said, neutrinos are all over the place. They actually had an influence on the growth of the structure that we see in the universe today. And by making these observations with telescopes and looking at the growth of structure, in other words, how did all the matter collect that we see, you can actually get information on the mass of neutrinos. And this looks to us to be one of the best ways in the near term of learning about neutrino properties. So what a wonderful connection that these things have, and it's really going to accelerate progress, we think.
Dr. Locke, anything quickly?
Yeah, quickly I'll just say supernova is when a star dies and collapses, and sometimes you create what's called a neutron star, and during that process you emit lots of antineutrinos. LBNF would be waiting there ready to observe those, and we would see thousands of them, as opposed to what's been observed so far from a famous event, 1987A, we saw 10. And so the difference in scale is now humongous.
Great. My time has expired. Recognize my colleague, Congressman Lipinski, for 5 minutes.
Thank you. And unfortunately, I don't have the time, so I won't be taking 5 minutes right now. I just want to make sure that I thank all of you for the work that you've done, the work on P5, which I think is extraordinary and really helps to sort of light the way of where we need to go. And I assure you that, yes, probably everyone on this committee who's not from Northeastern Illinois gets sick and tired of hearing Randy talk about Fermi. So he certainly does probably every hearing that we have, does a good job with that, and about high energy physics in general. But thank you for your work, and I was hoping that the chair would still be here, and I was going to recommend to her that we do a congressional committee trip out to Fermi, out to the Bay Area, because there's no two better places to go than to the Chicago area and the Bay Area. I've been to Fermi, I've been to SLAC, I've been to Lawrence Berkeley. I'd be very happy to go back out there, and happy to take a side trip to Santa Cruz also. I've been to Santa Cruz, not onto the campus, but I've been to Santa Cruz Boardwalk a few times. But thank you for your testimony, and thank you for all the work that you're doing.
I think that's a great suggestion, and I'll echo that as well to the chair. I do want to thank the witnesses for their valuable testimony and the members for their questions. The members of the committee may have additional questions for you, and we will ask you to respond to those in writing. The record will remain open for 2 weeks for additional comments and written questions from members. The witnesses are excused, and this hearing is adjourned. Thank you all.